there's like audio and all sorts of mad stuff, and I'm amplified, and they've hugely overestimated the popularity of this talk. Anyway, so yes, this is how JavaScript happened. And if into that you are reading a subtext of, and how can we stop it happening again, then you're not wrong. Although, so I'm going to cover quite a lot of programming languages in this talk, and I'm going to say some mean things about some of them, but I would just like this disclaimer. This is Flon's axiom. There does not now, nor will there ever, exist a programming language in which it is the least bit hard to write bad programs. Because it doesn't, you can make any program, and I think this follows on quite nicely from David's talk actually about intentional programming and how we write code to communicate with each other, and kind of also with machines, but mainly with each other. And so we're going to see lots of attempts at making programming languages that we can use to say, so this is what I'm doing here, and so on. But yes, you can write good programs in PHP. You shouldn't, but you can. And you can write bad programs in Haskell. That's the one that everyone seems to think is perfect, or Rust. I know you can write bad programs in Rust. I've done it. Anyway, there was a time before computers. And in the before times, people tried to invent computers at various points, and probably the best approach was in the 19th century. And Charles Babbage invented the difference engine, went to the UK Parliament and said, I need £500,000, which was a lot of money in those days. These days in the UK, £500,000 will buy you a potato. But he said, I need £500,000, I'm going to build a machine that does maths. And they went, that sounds interesting, here's £500,000, go off and do it. And he got halfway through, and then he had a better idea for the analytical engine. And so he went back to Parliament and went, scrap that, give me £1 million. And I think we've all been at that stage in a project. But this is not Charles Babbage, this is Ada Lovelace. Ada Lovelace was the daughter of Lord Byron, the famous romantic poet and syphilis incubator. And her mother, very sensibly, decided that the best thing she could do for her daughter was to keep her the hell away from her father. And so she sent her off to school, and she learned mathematics and engineering and science, and then she went to the salons where clever people got together and talked about clever things. And at one of those salons, she met Charles Babbage, and they became friends, and he showed her the analytical engine and how it was going to work. And the machine didn't exist, but she understood how it was supposed to work, and Ada came up with this notation for how you would describe a program that you were going to run on the analytical engine. So this is the first computer program, and in a sense, it's the first programming language. It's the first way to describe to somebody how to get a machine to do a thing. And she did all that before she was 37, because she had to, because then she died. Very sad. But actually 37 in 1852, not a bad age. And then from 1850 to about 1940, nothing happened. People built sort of calculating machines and all this sort of stuff, but we got to like 90 years of not really much progress. And then the Second World War came along, and Britain, entirely by itself, with no help from anybody, took on the combined might of everyone else in the world. And sorry, I've been listening to Boris Johnson. But no, so there were the goodies and the baddies, okay? And the baddies were communicating with each other using this. This is an Enigma machine, and into an Enigma machine, you type your message, and it scrambles it into different letters, and then you send that, and then on the other end, they have an Enigma machine that's configured the same way, and this changes every day, and if you type the scrambled letters in, then the unscrambled letters come out. And they thought this was uncrackable. They thought this was a completely secure way of doing it. But Polish scientists and then British scientists picked up the work, invented this machine called the bomb, and this is essentially a lot of Enigma machines all crammed into one space. It's like a sort of virtual machine host. It's Hyper-V for Enigma machines. And it just crunched through until it came up with some text that contained the word Hitler, and then it went, that's probably it. And so that was that was at Bletchley Park in the UK, which was a very important place in the history of programming. But then they started using this machine instead, and this is the Lorenz cipher machine. And the Enigma machine, the later versions of the Enigma machine, had as many possible combinations as there are atoms in our solar system. The Lorenz cipher machine had as many possible combinations as there are atoms in the observable universe. So, a lot. And they couldn't solve this with a bomb, and so they built this, Colossus. Guy called Tommy Flowers, who actually worked for the post office, and his trade was building telephone relays. And he built this machine with the help of Alan Turing and a whole bunch of people. And this is what we used to crack Lorenz ciphers. And then at the end of the war, we smashed it. And we destroyed it, and we hid all the records, and nobody knew anything about any of this until the late 1990s, when the records were unsealed and the Official Secrets Act stopped applying. And so nobody knew that we had built this basically a computer. And so what people think, or thought, was the first computer, really, was the ENIAC. This is the Electronic Numeric Indicating and Calculating Machine. And this was programmed by plugging cables between sockets on the thing. It worked like a telephone switchboard. And because it worked like a telephone switchboard, the people who built it went, well, the best people to program this will be women. And so they went, women, we've built you a thing. It looks like a telephone switchboard. Program it. And the women went, how? And they went, we don't know. Figure it out. And so the women, they actually had to figure it out from first principles, and they got it to work. Integrator and computer, so electronic, numerical, integrator, and computer. So these were the ENIAC programmers. But there was still, this was hardwiring a machine to do something, and then turn it on, and it would do it, and then turn it off again, and then hardwire it to do something else. There was no concept of a stored program. That came along with the IBM 701 mainframe. And this was in the 1950s. You could load programs into memory in the computer and then run them, and then results would come out. And that was great, and it was very powerful. And because people were still thinking quite a lot about war and warlike things, one of the things it had to be used for was like calculating ballistic trajectories. So if I fire with this much explosive at this angle in this direction, then where will the shell land? Will it be on... I'm not going to go there, actually. But, secret bunkers and hospitals. The problem, though, was that to program the IBM 701, you had to take that trajectory formula, and I'll be honest with you, I didn't do a lot of maths. I don't even understand what x equals tan theta minus gx to the power of 2 over 2v to the power of 2 cos squared theta. But you had to take that maths, and then you had to translate it into machine code. And this is an example of some machine code from the IBM 704 machine, and actually it's those org, LXA, CPY, all those things going down there. And so it was difficult. Programming was difficult. And this chap came along. This is John Beus. And he was just walking past the IBM building in downtown Manhattan, and he looked through the window, and he saw the IBM 701 that they had on display in their lobby. And it's had all flashing lights all over it. You know when you see those computers in the past, and they had all the flashing lights on them? Do you know what those were for? Selling computers. Most of them didn't actually do anything useful. I mean, they did have a meaning, but they didn't do anything useful. It just made people want the computer. They always got flashing lights all over it. I want those. So yes. So John Beus joined IBM in 1955. He went, do you have any jobs? And they went, you could be a programmer. And he said, what's a programmer? And they said, we're not sure. And he went, yes, no, okay, I'll do that. And then he went and he found out what programming was. And this was in 1955. So this is basically the same year that the first McDonald's opened in Illinois, and Disneyland opened, and Kermit the Frog first appeared on TV. And they went, you take this trajectory formula and you translate it into machine code. And he went, oh, that sounds difficult and slightly boring. I'm not sure I want to do that, because John Beus, bless his heart, was lazy. Hands up who's lazy. Yeah. Lazy people make the best programmers. Bill Gates says, I choose a lazy person to do a hard job because a lazy person will find an easy way to do it. And John Beus immediately thought, well, I've got a machine here that takes an input and produces an output. So what if the input was the formula and the output was the machine code, and then I feed the machine code back in over here, and then it runs it, and then the output is the answer to the formulas. It's a sort of two-step process. And he went to IBM and went, I've had this idea. We're going to sort of translate formulas into machine code automatically. And IBM, very weirdly, to this completely new guy that they didn't really know, went, yes, here's a team. And they gave him a team of people. And they bounced around various IBM offices while they were building this thing, and they created Fortran. And Fortran came along in 1957. And Fortran was the first high-level programming language. 1957, that's the same year that Sputnik 2 launched with Laika, the dog, on board. Moment silence for Laika. That'll do. So yes, this is FizzBuzz in Fortran. So we have our loop is do. Well, first we have to say program FizzBuzz. Our loop, we do, and then 40 is the line number, so that's pointing down to the bottom there. I equals 1, and then go to 20. And then we say if mod I15 doesn't equal 0, go to 20. Otherwise, print FizzBuzz and continue will go back up to the loop top, back to the do, okay? And then we got 20, if it's not 5, then go to 30, otherwise print buzz. 30, if it's not 3, go to 40, otherwise print fizz. Otherwise, print whatever the number is, and then because our 40 matches the 40 up at the top there, we loop back to the top, okay? So that is FizzBuzz in Fortran. This is factorial in Fortran, just for fun. But you'll notice one thing on this slide, n times I. So the initial specification for Fortran was going to use the multiplication symbol. And then somebody went, I haven't got the multiplication symbol on my punch card typewriter. And they went, what have you got? Got an asterisk, it looks a bit like it, and so they replaced it with the asterisk. So that's why we still use the asterisk. And Fortran, there was no terminal, there was no sort of like typing the code in and everything. There was punch cards. This is a line of code on a Fortran punch card. Every Fortran punch card was a single line of code. There were 80 columns. That is why the first dumb terminals had 80 columns, and it's why in Visual Studio the word wrap is still by default set to 80 columns in 2023. Or it was the last time I checked. I use Rider. So yes. But Fortran gave us the if statement, it gave us the asterisk for the multiplication operator, and it also gave us I as the iterator variable. So every time you write a for loop, you write for int I equals 0, I is less than whatever, I plus plus. And you sort of think, why I? And a lot of people think it's because I is commonly used as the sort of numeric symbol when you've got a repeating sequence in mathematics notation. Hands up who knew that. Yeah, see, it's not that. It's because in Fortran there were two data types, integer and real floating point numbers. And if you wanted a variable to be an integer, the variable's name had to start with I, J, K, L, M, or N. And if you wanted it to be real, it had to start with any of the other letters in the alphabet. And so if you wanted to do a loop with an integer, then I was the obvious thing, because that's what it's an integer. Later versions of Fortran actually allowed you to declare variable types, which led to the hilarious programmer joke, God is real unless declared integer. No, don't laugh at that. Anyway, Fortran went out there, and then this guy looked at Fortran, and this is Edgar Dijkstra, however you pronounce his name, Dijkstra. And he said a lot of things about programming, but the thing he said about Fortran was GoTo considered harmful. He wrote a whole essay called GoTo considered harmful, saying you're jumping around all over the place and it's just hideous. I also found another quote from him, which I really love. If debugging is the process of removing bugs, then programming must be the process of putting them in. Hell yeah, that's what I do all day. And so a bunch of people got together, and this was the first programming language that was designed by committee, ALGOL. And ALGOL appeared in 1958 just as a specification. There was never a sort of really useful implementation of ALGOL 58, mainly because it didn't have I/O. So you had to write a program with all the variables already set to their values and then run it, and then inspect the content of the memory registers after it had finished. So yes, but ALGOL had things like loops and conditionals and functions and that sort of stuff. And so here we have FizzBuzz written in ALGOL. And you see we've got for I colon equals 1, step 1 until 100 do. And then we've got begin and end, saying this is the start and end of our loop here. And then we've got if, then, elif, else. And we've got outstring, which is a function, which this is ALGOL 60, by the way. And outstring is a function which writes out to the standard output. And you'll see at the end of the outstring lines and the integer line and so forth, we've got semicolons as well. ALGOL introduced the idea of semicolons. And another interesting, so John Beus was on the committee that designed ALGOL. So the guy who designed Fortran, they went, you know stuff about this, so help us with ALGOL. And he came up with a syntax for describing programming languages, which we still use today, BNF, Bacchus-Noor form. Was called Bacchus normal form, and then Peter Noor, who was also on the committee, who had contributed something to it, somebody went, no, it's not really normal form, according to Chomsky. And Peter helped, so why don't we call it Bacchus-Noor form? So we did. And so this is an ALGOL 64 statement in BNF grammar. And this is a JavaScript looping statement for the various versions of for that JavaScript has in BNF grammar. We still use BNF, an extended BNF, as our way of describing programming languages and also building parsers to this day. So from ALGOL for JavaScript, we get block structure, the sort of begin-end thing, if then else. ALGOL had switch statements or case statements in some languages, for loops, functions, semicolons at the end of lines, and Bacchus-Noor form for describing the language itself. There were many, many spin-offs of ALGOL. It never really took off. It was a very kind of theoretical language. It was like the Platonic language that other languages learned from and drew inspiration from. One of those spin-off languages was called ALGOL W. which introduced the concept of records and references to records. And when you have references, then what do you have? Null. Thank you, Algol W. Tony Hoare's billion-dollar mistake, and I think it's probably a lot more than that. But yes, this is not FizzBuzz, but this is an example of Algol W where you have the null keyword. So Algol was kind of structured, and you can sort of see how block syntax and so forth fed into other things. The other language that came along in 1958 was Lisp. And Lisp was created by John McCarthy at MIT. He thought it would be a really good language for writing artificial intelligence systems in, because he thought they were about 2 years away from having computers that could think like people. And I think now we're about 2 years away from having computers that can think like some people, but that's only because some people are really fucking stupid. I'm British, I know. I live with them. So yes, hello Britain on YouTube later. Have at it, I don't care. So yeah, this is John McCarthy, and he created Lisp on the IBM 704, so the same system that Fortran was intended to write on. This is FizzBuzz in Lisp. Lots of parentheses. You can always see when somebody's programming in Lisp because they're programming with one hand, and then on the other hand, they're using the 12-based counting system to work out how many parentheses they need to close when they get to the end of their code. But yes, this is FizzBuzz in Lisp. Has anyone done any programming in Lisp or a Lisp, like a scheme or anything like that? Because there's a couple of really weird operators in there. Lisp works on lists, okay? And so everything between brackets in here, like mod n3, is a list that contains the mod operator and then the n atom and the 3 atom, which are values. Now, if you wanted to get the first item off that list, you would use a command car, C-A-R, okay? And if you wanted to get the rest of that list, you would use coulda. And car and coulda are famous in Lisp circles and scheme circles and all this sort of stuff. They're still used to this day. Doesn't matter where your implementation of Lisp is. I think Closure actually has car and coulda in it. This is a brilliant example of where the implementation details leaked into the language itself, because this is an IBM 704 register. So IBM 704 had 36-bit registers. And one of the common uses for them was that you would have a prefix and then a decrement value and then a tag and then an address value. And this was just part of how you programmed machine code in there. But when John McCarthy wrote Lisp, he had a heap, and he had objects created, he had things created on the heap, and so the decrement register, the address register pointed to the first item in the list, and the decrement register pointed to the rest of the list. And so that would point off to somewhere else in memory, which had the second item in the list, and then the pointer to the rest of the list, which was the third item, and so on and so on. So a linked list. So car is content of address register, and coulda is content of decrement register. And the IBM 704 is the only machine that ever had Lisp on it that had an address register and a decrement register, and yet we still call it car and coulda. So I love that. But Lisp introduced the idea of first-class functions. So functions can be in a list of things that you pass to other functions. You can throw things around. It was the first programming language with a heap, because everything in these lists was pointers to either single values in memory somewhere or the rest of the list. And because it had a heap, it had garbage collection. There was a guy, one of John McCarthy's grad students, wrote the garbage collector for Lisp. And it sort of had a JIT, because you were throwing functions around the place. In order to have first-class functions, you had to pass around the representation of the function. And so it had to be able to compile functions on the fly. So it was more sort of a compile on the go. It wasn't really a JIT, but we'll come back to that. Okay, 1962, Simula, invented in Norway at the Oslo Institute of Technology or somewhere like that. Simula was the first object-oriented programming language. So this is FizzBuzz. I mean, it's a torch. You can write FizzBuzz in Simula much more easily than this, because you can write it just like you would in Algol, but this is demonstrating Simula as an object-oriented language. But yes, previously, when I've done sort of various talks, and you say, what was the first object-oriented language? And a hand will go up and they'll say Smalltalk. It wasn't, it was Simula. And so yes, this is FizzBuzz in Simula. So Simula introduced the idea of classes and all the object-oriented concepts that go along with that, like inheritance, polymorphism, and scope, like hidden variables, protected variables, internal variables, all that sort of thing. And then in 1967, there was APL. APL, I've shown it as kind of inheriting from Fortran because it inherited the idea of being a programming language from Fortran. But there's never really been anything else quite like APL. It was invented by this guy who taught computer programming. This is Kenneth Iverson. And he said this: a notation must allow convenient expression to be effective as a tool of thought. So APL, which incidentally stands for a programming language, yeah, naming things. one of the hard problems. So yes, he created APL, a programming language, to use to teach his students programming. This is FizzBuzz in APL. Yeah. The thing with APL, and this is actually a really good thing about it, it works on arrays. And so you don't say, do this, loop round and do this for it. You just go, do this to everything in this array at once. And it will parallelize it. It will, the compiler can do all sorts of magical things with it. But it also uses these weird little Greek characters. And so if you wanted to program APL, you had to buy this keyboard. I don't know if Kenneth Iverson sold them for like $500 and they were a prerequisite for his university course. If he didn't, he should have. And so, yeah, that's FizzBuzz in APL. The main thing that APL introduced that didn't exist prior to APL was that the types in here are dynamic. And so it's kind of got this, it's an array, and every element in the array could be an integer, it could be a real, or you could have a different thing in all the different elements of the array, and you can do interesting things with it. I don't seem to have the slide. I had to reconstruct my slide deck from a YouTube video because I lost the laptop that the slide deck was on. Also, I'm wearing yesterday's socks because after this talk, I have to go and get my luggage from the airport. So I've been having fun. But Game of Life in APL is only like 10 characters longer than that, Conway's Game of Life. It's a ridiculously terse language, but it had dynamic types. Okay, in the 1960s, we had B and BCPL and CPL. So CPL was control process language, BCPL was batch control process language, and B was just a simplified version of BCPL. And this is FizzBuzz, written in one of those. And you'll see here that we've got the curly braces. This was the language that introduced curly braces. And everywhere, instead of begin and end. Except that this was in the 1960s, and the ASCII character set that they had at the time, 7-bit ASCII character set, didn't have curly braces in it yet. This actually came out in the same year as curly braces were added to the 7-bit ASCII character set. And so they went, okay, well, if you have a machine that supports the latest version of ASCII, then you can use the curly braces. Otherwise, you can use $open paren and $close paren. It's like Lisp with money. So yes, but BCPL gave us curly braces. And then out of BCPL and B and so forth grew C, 1972, the year before I was born. I learned programming from this. Well, actually, I learned programming from the ZX81 user manual, but I learned proper programming that you could get paid for from this book. This is the first edition of the C programming language. And this was the first programming tutorial where the first thing it taught you how to do was print hello world. And that's historical. This is FizzBuzz in C. I expect most people in here can read that with no trouble at all. Looks just a lot like JavaScript or C# or Java or whatever. This, however, is also FizzBuzz in C. This is from the International Obfuscated C contest, where it is a competition that happens every year, where the point is to write a C program that looks ridiculous, like just a jumble of characters, but it actually does something useful. So this is Obfuscated C doing FizzBuzz. And this is Obfuscated JavaScript doing FizzBuzz. Dylan will be able to explain how that works, and he loves explaining it. So yes, from C, we got what we now recognize as C-style. We talk about C-style programming languages. We got the idea of hello world. We also got truthiness. So if I just go back to here, you see, you can't see my cursor, but the first if statement, we've got if not I mod 15. And so C will take the 0 as false and any non-zero value as true. And so we got this idea of truthiness from C. We also got the idea of obfuscating code for fun and profit. Fun, because it's fun and it shows how clever you are. Profit, because if you do it at work, they can never sack you, theoretically. Also in 1972, we got Smalltalk. Smalltalk was created by some people at the Palo Alto Research Center, which was owned by Xerox. And Smalltalk was kind of designed and built at the same time as the first GUI. And so we got to this thing where we weren't just printing characters to a screen, we had objects moving around on the screen, and users could click on different ones, and so we had to be able to respond to events rather than just providing options and letting users choose something. They could click anything at any time, and you had to be able to deal with it. And that lends itself very well to being written in an object-oriented language. And so Smalltalk was designed as the object-oriented language. And the idea was that events would be messages. And so the user could click something, and that would be a message, and the message would be sent to the thing that the user had clicked. And you can still see this in Windows programming in C and C++. You've got WM_click and WM_DBL click, Windows message, window message. And so Smalltalk introduced this idea of message passing between objects as a way to build systems. And, you know, Alan Kay, who coined the term object-oriented programming alongside Smalltalk, has said, I wish I'd called it message-oriented programming, because the idea that you have a dog that extends animal isn't really the point. It's that the dog should send a message, bark, to a human to say, feed me. So yes, this is Smalltalk, FizzBuzz. And what this is actually doing is adding a FizzBuzz method to the integer type. Any Ruby programmers in the room? Ruby is, you know, people go, oh, why did Smalltalk die? It didn't. It just moved to Japan and became Ruby. And that's a really, you know, I love Ruby. Ruby is a fantastic programming language that runs extremely slowly, and Rails is a tire fire. But the stuff that it took from Smalltalk, if Ruby objects can define a method called method missing, and then any calls that, any messages that are sent to that object that the object isn't expecting will be diverted to this method missing thing, and you can make it do magical stuff. So much of Rails works like that. So this, in Smalltalk, adds a method called FizzBuzz to the integer type, so that if you then say, send the message FizzBuzz to any integer, it will do what is inside this method declaration. And you can see it being called down at the bottom there. So for all the integers from 1 to 100, call it I, and then pass the message fizzbuzz to it, and then pass the output of that to display NL. Also, this. Since all values are objects, classes are also objects. Each class is an instance of the metaclass of that class. Metaclasses in turn are also objects and are instances of a class called metaclass. Yeah. So, from Smalltalk, we get the idea of reflection. Smalltalk was the first language where you could inspect the code at runtime and the objects at runtime and do interesting things with them. It was the first thing that had a debug output, so it had a console that you could write to that wasn't part of the main thing. And it was the first thing that had a virtual machine and a proper JIT compiler. So Smalltalk code was compiled to an intermediary form, and then that was distributed, and then it was JIT compiled on the target machine. And also this idea of everything being an object, which obviously JavaScript lent into hard. So I say Smalltalk was the first thing with a proper JIT. It actually wasn't. The first language that had a proper just-in-time compiler was actually regular expressions in 1968. So regular expressions have been around for ages and ages, but in 1968, they were sort of used by the guys behind C and grep and all Ken Thompson and Dennis Ritchie and Brian Kernighan. They made an implementation of regular expressions for their QED editor, and then it also went into awk and grep and sed and things like that in Unix. And I thought, I'll have a quick look. But the regex implementation in 1968 effectively had a JIT inside it. So it compiled the regular expression into a series of kind of machine code instructions, and then it would compile that to the native machine. This is fizzbuzz in regex. Yeah, thank you, Stack Overflow. I have no idea how that works, but apparently if you just have the numbers 1 to 100 in a text document, and then you run that regex over them, it will replace the 3s with fizzes, the 5s with buzzes, and the 15s with fizzbuzz. Yay. ML. So this was came out of Lisp. This was a functional programming language, and there are lots of languages around today that are still basically ML, because ML became Camel, and then we got OCaml, which was Camel with objects, and then we got F#, which is OCaml with .NET. And so this, outside of Lisp, this really created the direction for functional languages. So this is fizzbuzz in ML, and you can see here that we've got the arrow operator, the equals greater than, and it also has minus greater than, but the arrow operator came from ML, the arrow function syntax. Then we got Scheme. Scheme was created at MIT for teaching the Computer Science 601 class by Abel and Sussman. It was a simplified version of Lisp. It's very, very quick and easy to write a scheme. And this is fizzbuzz in Scheme. Looks very similar to fizzbuzz in Lisp, except, like I said, it's slightly shorter there. Yeah, but essentially it's a Lisp. The thing that Scheme donated to JavaScript is that when they went to Brendan and said, hey, write a programming language in a week. And he went, right, well, that's going to be a scheme then. And like 2 days later, he went back and I've done it. And he basically just made Scheme run in the browser. And they looked at it and went, no, you have to make it look like Java. And so, in a way, what Scheme donated to JavaScript was the name JavaScript. Because otherwise, it would just have been called like browser script or Netscape script or something. But yeah. Then we got C++. From the man who invented it himself, C makes it easy to shoot yourself in the foot, C++ makes it harder, but when you do, it blows your whole leg off. Absolutely true. This is fizzbuzz in C++. I remember sort of people, I was programming in C for a living, and then they went, oh, C++. C++, we have to move everything over to C++ now because Windows and MFC and all these sorts of things. And you go and you do hello world in C++, and it's cout less than hello world semicolon. And you're just like, why have you done this? Nobody wants this to work like this, but apparently some people do. But yes, there's not a lot, you can't see in the FizzBuzz example, but what C++ introduced was the idea of exceptions and exception-based flow in your program. So try, catch, and throw, and exception handling generally. So these things had existed in some frameworks, some libraries for other languages, but C++ was the first programming language that actually had them built in to the language itself. Has anyone ever heard of a programming language called Self? I hadn't until I started researching this talk, but you go through sort of various family trees of programming, and Self is in there as a precursor to JavaScript. So Self, it kind of took some ideas from APL, dynamic and that sort of thing, but it was the evolution of Smalltalk. And so some people who had worked on Smalltalk went to Sun, and they worked on Self. And Self, it's really difficult. God knows what FizzBuzz in Self would look like. This is the programming environment for Self. But it's, the thing that Self introduced was the idea of object-oriented programming with prototypes instead of classes. So you didn't have a class, you had a prototype, and then when you created an instance of an object, it would take all its initial state from that prototype. And then you could have a prototype that took its initial state from that prototype and modified it. And you know the hideous, awful, terrible way JavaScript does object-oriented programming. So that came from Self. There was a bunch of other stuff in there as well, like JITs and VMs and sorts of things, and it actually evolved into Java in 1995. Java didn't take a lot from Self, so I'm not linking it there. It was obviously based on C++. Yeah, some of the Java was kind of, they went, oh, Self's not working, it's not going to work, we don't like it. Do this instead. And so then James Gosling created Java, which was released in 1995. This is FizzBuzz in Java. Yeah, that is supposed to be funny. We've got a sound factory there. I found larger implementations of FizzBuzz in Java, but they didn't fit on the screen. And I thought I could make it scroll now. But yes, so Java, and the main thing that Java sort of donated to JavaScript, as I mentioned previously, is the syntax. Make it look more like Java. The reason for that, incidentally, was that the